welcome everyone to day 5 of the NOAA Satellites Hackathon. And today we are doing our training on the coding workshops. So we're going to do some Google Colab and Google Earth Engine walkthroughs. So after you've learned everything this week, on Monday you learned about the geostationary Earth orbit satellites and products. On Tuesday you learned about the low Earth orbit satellites and products. On Wednesday, you learned about the space weather satellites and products. Yesterday, you learned about science communication, a little bit about social science, how to make your scientific message reach your audience. And today is the coding workshop. So hopefully after this whole week of training sessions, you'll have all the introductory material you need to get started on your projects next week. And most of our trainers will be hanging out in Slack as subject matter experts so that you can ask them more detailed questions once you get started on your projects next week. But for now, let's get started with our coding workshop, starting with Diego Souza, who will be telling us about the visualizing of Earth imagery data using Google Colab. So take it away, Diego.
Okay, let me share my screen. Can you see it? Can you see my slides maximized?
Yes, thank you.
Okay, thank you, Katie. Okay, hello everyone. Good afternoon. My name is Diego Souza, and I'm an engineer at NPA, the National Institute for Space Research in Brazil. And today I will be presenting how to access, process, visual goals and JPSS database find on Google Colab. First of all, I would like to thank Katie and the organizing committee for the invitation. This is a third hackathon I have had the opportunity to participate in, and it's always a great experience. And this is the objective of this presentation, okay? First, we'll learn how to download data from any satellite in the GOES-R series, GOES 16, 17, 19, and 19, for any date, instrument, and product available on Amazon Web Services using a simple, easy-to-use Python function like this one, okay? You just need to insert the date, the GOES satellite, the product, the band, and the location where you want to save the file. And once downloaded, you'll be able to process these files using Python and Colab. Next, we will learn how to access JPSS data, including NPP, NOAA 20 and 21, for any date, and VIRS band available in Google Cloud. Again, using a simple Python function where you just need to inform the satellite, the VIRS band, the start date and the end date, and all granules between those dates will be downloaded. Okay, and we'll show you how these files can be processed using a software called Polar to Grid, developed by the University of Wisconsin. And all this processing will take place entirely in the cloud using Google Colab, so you won't need to install anything on your local machine. However, all the examples also work if you want to read them locally. Okay, and this is the main idea, to enable you to download and explore GOES-R data in just a few lines of code, like in this example, where we download a GOES-R file for a specific date, satellite, and product. We open the file and read the data variable, and we configure and visualize the image. And you can repeat this process for the dozens of GOES-R products available in the cloud. Okay, and here we have another nice example using the functions we will see today. We can easily download a netcdf file from SUVI, for example, the Solar Ultraviolet Imager aboard the GOES satellites. And in this case, we are downloading an example showing a coronal hole here directed toward Earth. And when the solar wind reaches our planet, it can trigger geomagnetic storms and produce auroras. And we can observe here this effect in the image from the VIRS day-night band from 21, which was also accessed and processed using Google Colab. Okay, so that's the idea. And to provide some context, we will start with a brief introduction to the data access and processing, Then we will see how to access GOES-R data available on Amazon manually, followed by a demonstration of a Colab notebook showing how to do the same, but using scripts. And we will repeat this process for JPSS data, first accessing it manually from Google Cloud, and then demonstrating a notebook to automate the process using scripts. And finally, we will wrap up by sharing additional resources and references. And this slide deck and the two notebooks we will explore in this first session are already available in SCAD. Okay. This is where I work, and this photo shows our coordination office here in Cachoeira Paulista, which is a city in the state of São Paulo in Brazil. And in our meteorological satellites division, we focus on scientific research using data from meteorological satellites. And we develop satellite products, and we generate these products operationally for the Brazilian and the international communities. And we also have experience in satellite data reception, dissemination, and visualization, which is the focus of our presentation today. And just to provide some context, one of the many benefits of the current generation of satellites like GOES-R and JPSS is how much easier it has become to receive and process satellite data. About 10 years ago, before GO16 was launched, the available options were much more limited. And here in this example, we have a picture showing a couple of antennas receiving GOES-13 data here at NPay in 2013. And back then, we relied on proprietary solutions. The file format was not as straightforward to process, so it was a much more complex process. Okay, but thankfully now we have many more options available. Here's an overview of some of the available data reception systems. We have the direct readout and rebroadcast services where our antennas are pointed directly towards the weather satellite of interest, whether GEO or LEO satellites, or towards a commercial satellite broadcasting data in near real time. We also have the internet-based mechanisms that we are going to explore today, where data providers such as NOAA provide data for free in near real time. We also have the long-term historical archives from NOAA, for example, with literally decades of data sets available for download. And we have many web pages providing imagery already processed. So we have plenty of options now, right? And today we are going to explore Amazon and Google Cloud, okay? Also, data processing has become much easier as well. For example, there are many libraries, many Python libraries available for handling satellite data. And in our visualization systems developed here at NPay, for example, we use some of these libraries, and thankfully they are very well documented, and we have plenty of examples available online, as we are going to see. And even though there are other programming languages and processing tools available, over the years, Python has become the most widely used tool in community for processing data from GEO and LEO satellites, as we can see here in the results of a recent regional survey conducted by WMO. So we have been using Python extensively here in our regional training sessions. Here are some examples. We have organized hands-on activities on GEO satellites, LEO satellites, NWP, ocean, weather radars, and much more, all using Python. And relying on a single tool has greatly simplified the process. As in the past, we needed to work with multiple different software programs to have the same results, to achieve the same results. Okay, so today we're going to learn how to download data from the cloud, okay? And NOAA has an initiative called NOAA, the NOAA Open Data Dissemination Program, which make NOAA's vast collection of data freely available and openly available to the public through cloud service providers like Amazon, Google, and Microsoft. And we won't go into much detail today, but on this slide, you'll find a very nice reference about this program to explore later. It's an AMS short course. Those are JPSS satellite data and tools available through cloud service providers. Okay. And at this link here, you can find a list of hundreds and hundreds of NOAA data sets that are available through cloud service providers. Okay. And it is really impressive. Just look at the amount of information available. We can find data from NASDIS, from the National Weather Service, from the National Ocean Service, and others. And today we are going to explore the GOES-R and the JPSS data available through the NOAA program on Amazon and Google Cloud. Okay, and as we are going to see, it is not hard. Let's begin with GOES-R data available on Amazon. Okay, on AWS, for example, there's a dedicated web page where you can access these repositories or buckets, as they're called, with hundreds of GOES-R files or thousands of GOES-R files. The same page has many usage examples and tutorials, which we definitely recommend to check out. And once you click on Browse Bucket, you see a set of folders, each corresponding to a specific GOES-R product, okay? And inside each folder, there are subfolders by year, Julian day, hour, and finally, yellow files for that hour. And clicking on a particular file will download the file directly to your machine, okay? It's very easy. Let's make a quick demonstration. Let me open my browser. Let me access the AWS page for GOES-R, and here it is. You have the link for GOES 19, GOES 18, GOES 16, and 17. And here you have the usage examples. Let's click on Browse Bucket for GOES 19. And here you have each one of these folders is a different product, okay? And let me click on CMIPF, which are the bands already in brightness temperatures for the full disks, which cover Brazil, 2025, Julian day number 283, which is today, 19 UTC, and here we have files for this hour and for different bands. And if I click here, for example, on file for band 30, it will download this file to my computer, and I can process it the way I want. Okay. Okay. But you can do this manually, as we have seen, but we can also use Python scripts to automate the process, as we will see in this Colab notebook. Okay. A Colab notebook is basically a virtual machine running Linux with Python already installed, and it allows you to add text cells and code cells. It allows you to install Python libraries, run scripts, and so on. We won't go into much detail about Colab today because we don't have time, but you can check out this 1-hour video from previous hackathons, which covers a lot of information about Colab, including what it is, how to create a notebook from scratch, and how to process GOES-R data in more detail, okay? But let's go to the demonstration. Here we have our Colab notebook for this first demonstration. And if you access the SCAD page, you can just click here. It will open this notebook, okay? However, the first thing we need to do is to create a copy here. File, save a copy in Drive. This will save this Colab notebook into your own Google Drive. So you are able to edit, make changes, save, and do anything you want. If you run the original, you won't be able to save it, okay? So the first thing is to create a copy. File, save a copy in Drive. After some seconds, it will open the copy on a new tab. So this here, it's a My Copy. Okay, this is not the original notebook. Okay, I'm working with my own copy, right? So that's why I have added here Diego underscore the original, the notebook. Okay, so here we have an image, and this image is on text cell. We can add text cells. This is the text to document our code, or we can add code cells. Okay, print NOAA hack set, for example, and run this cell. It will print my message. So this is a text cell and this is a code cell. And I have added here some text cells and code cells that are ready to use. So you don't need to worry about creating the code from scratch, okay? Here on the left side, you have the table of contents where you can navigate through the topics we have created for this example, okay? And you can also click here on files and check the structure of the virtual machine, okay? Okay. The first thing we do in this example notebook is installing our Python libraries. All the commands starting with a exclamation mark, it's a Linux shell command, okay? So here I'm installing, let me zoom in a little bit. Now it's better. So here I'm installing 3 libraries, okay? Dodo3, which will make our connection to the Amazon Web Service bucket. XArray, which allows us to read a .cdf file, and Cartopy, which allows us to add maps, okay? So if you click here, this cell will be executed and these libraries will be installed, okay? The second thing we do is creating folders, and I'm creating 2 folders, one called samples, which will store our .cdf files, and one called output, which will store our PNGs generated with our scripts. And these folders are here, samples and output. I could create, for example, another code cell and create another folder, for example, NOAA accept. And it should appear here. It's not appearing for some reason. Oh, sorry. Here it is, NOAA accept. Okay. So you can run any Linux command you want. Okay. The next thing I do is I will import a function for downloading OSR data. Okay, so I'm using the wget command to download a script that is available on my GitHub account. And this script is called downloader.py, and inside this script there's a function called download. And this is a big function that does the complicated stuff for us. Okay. Okay, and then with this function, I can download data from GO 16, 17, 18, 19, any instrument, any band, since these satellites have been considered operational. Okay, let's make a demonstration. Here, I will click on play, and this particular netcdf file from GOES 19, this particular product, which is the cloud and moisture product for Cronus, band 13, for this particular time and date, it has been downloaded and it is available on this folder here called samples. If I expand this folder, here it is, CMIPC, band 13, GOES 19, and this is the file for today, okay? October 10th, 2025, 16 UTC. Now it is 16, 17, 19 UTC. Let me change for 19, for example, and download it again. Downloading file, successfully downloaded this CDF file. And then I can use XArray to read the file I have just downloaded. I can use this instruction called open dataset and pass the file I have just downloaded, and I can check the characteristics of this file. For example, it says that it has 1,500 lines per 2,500 columns, It has 35 data variables, and if I expand here, I have these data variables, and the first one is the data variable with my brightness temperatures for the IR bands or the reflectances for the visible bands. Okay. Okay. So I also have the attributes. For example, goes east. This is a 2 kilometer band from goes 19 covering the Konos region. So I have everything I need to know about this file in the file metadata. Okay, and I'm reading this information with X-array. Well, after I open the file, I will read the data variable with X-array and pass the pixel values to a variable called data. So, and X-array showed me this information. Hey, the CMI dataset, which is the cloud and moisture imagery, which has the brightness temperatures or reflectance values, we have this number of lines, this number of columns, and a total of more than 3 million pixels. And these are the attributes for this particular data variable. It's an ABI, cloud and moisture imagery, brightness temperature variable. The units is Kelvin. This is the resolution, and this is the valid range for a pixel. Okay. So I can repeat this anytime the way I want. For example, let me download another file. Right now it's 1925. Let me download the file from 1920. Okay, downloading file, successfully downloaded. Open the file, create the data variable, and finally, I will create my visualization. Okay, this is a Commons image from October 10, 1921, which is 5 minutes ago. Okay, and I can repeat steps 4 through 7 the number of times I want and download all their data sets. For example, if I change here from ABI level 2 CMIPC to CMIPF, which is full disk, and download it again, it will download a full disk file. I can open it. I can read the data variable and create my visualization. It is a full disk image, so it takes more time to create the image. Okay. And here it is. This is a full disk image from 16 UTC today. Okay. I'm not going to explain in detail each one of these commands because we have added to our slides other resources that you can check explaining each one of these commands. But we are basically creating a new figure, 10 by 10 inches, and we are creating a visualization object with the data array, with this color map, and these temperatures as our minimum and maximum values. If I change here, for example, to jet and run the cell again, we will see the image in using another color map. Okay, so you have total control of your data array, and that's the magic of it. And I can change here to vertical, for example, to change the orientation of the color bar. So that's the thing. You've downloaded a file from Amazon. You are reading the 2D array, and you are manipulating and processing this 2D array the way you want. And please note that you have, if you change here for G16, for example, you have data since 2017. So there's plenty of data available. And I can also visualize the mesoscale sectors. If I click here, mesoscale sector 1, downloading, downloaded, read it, read the data array, and visualize the image. This is the mesoscale 1, the current mesoscale 1. So that's the idea of this Colab notebook. You can access it, create a copy, okay, and change it the way you want. But the nice thing about it is the download function because it really simplifies things. If I go to my GitHub account and go to my repositories, NOAA sat hack, there are a couple of files called downloader and downloader.jpss. And this downloader file script, it's complex, it's not easy, hundreds of lines of code that makes all this filtering, etc., but you don't need to worry. You just need to understand how this function works. Okay? Well, and we have added many examples below this one. Visual downloading, opening, and visualizing several derived products from those are cloud top phase, cloud top pressure, clear sky masks, the cloud masks, cloud top phase, cloud fraction, aerosol detection, and here I have the dust flag. Let me run it with the smoke flag, for example. That's the dust flag. I will run it again with this flag. If you want to detect smoke or dust, okay? Aerosol optical depth, and we have more than 20 derived products available on derived indexes and so on, okay? Each one of these plots is from a different GOES-R product, like snow cover, cryosphere ice concentration, land surface temperature, etc. Okay, and you can also download data from other instruments like the solar ultraviolet imager, as Marcial is also going to present. And by checking our reference files, you can learn how you can overlay GLM data with GOES-R, for example, to create nice plots like this one, where you have a mesoscale sector and GLM events, groups, and flashes overlay. Okay, so that's our first Colab notebook. Let me return to my slides. Okay, we have seen how to access GOES-R data from AWS, from Amazon Web Services, and now let's take a look how to access JPSS data on Google Cloud. In the Google Cloud Marketplace, you can search for NOAA, and one of the results will be the JPSS repository. And similar to what we saw on Amazon, there's a folder for each satellite here. One for NOAA 20, one for NOAA 21, and one for MVP. Okay, and once you select the satellite, you will see multiple folders for its different instruments, such as ATMS, CRIS, OMPS, or GEARS. Okay, and when you select an instrument or a band, the subfolders are organized by year and or just like on Amazon. And there are hundreds of files per day. And once you select a file, this file will be downloaded to your machine. Okay. Again, let's make a very quick demonstration. I'm going to access the JPSS repository on Google Cloud. This is the description, and here we have folder one for NOAA 20, 21, and SMPP. This is the directory for NOAA 20. You have a lot of folders with instruments and bands. I'm going to download a verse band I1 in this case for 2025, day number 10. Sorry, it's 10 and day number 10, which is today. And when you click a particular file and click it again, this file will be downloaded to my machine and I can process it with Python. This is an HDF file. We can use there are HDF libraries in Python, so you can use these libraries to process them. But we have created an example notebook showing how to process these JPSS information as well. Okay, this notebook, I will not run these cells because it takes more time to install for downloading files, because processing Leo data is more complex than processing Leo data. Okay, so I'm just going to describe what the content of the notebook. The first thing we do is we install Polar to Grid, which is a very nice software developed by the University of Wisconsin. So we install Polar to Grid. We check if Polar to Grid has been correctly installed. We install some dependencies. We install some additional libraries, and we also download from my GitHub a downloader function called download JPSS. Okay. We download some shapefiles and we create folders, one to store the samples and the other one to store the shapefiles. We import the required Python modules and functions. We authenticate Google so we can download information. And finally, we use the download JPSS function in this example to download data from NOAA 21 band I1 between this starting date and this ending date. All the granules between the start and the ending date will be downloaded, as we are seeing here. Okay, and then once they are downloaded, we can use Polar to Grid to process this information. Okay, Polar to Grid will say, hey, if you downloaded band I1, you can process and visualize the band I1. And you can say, hey, please create a geotiff from band I1. It will do it. We can add coastlines and visualize our information. It's taking some time, but I believe it's not showing because I have so many things opened. And you can download other bands from other time frames. It's not showing the images because they are so big, but you got the idea. Okay. Here's an example, right? Polar to Grid will make all the complex calculations, and it will mosaic these granules, make all the complex calculations, and generate a nice image for you in high resolution. In this case, 375 meters per pixel. But how do I know, as a low Earth orbit satellite, making multiple orbits per day, how can we know the exact time when a satellite passes over our region of interest? This is very important to know, and fortunately, the University of Wisconsin provides an interface where you can check the passes of many LEO satellites, including the JPSS ones. Okay. Here, NOAA 20, NOAA 21, and you can select a date, and it will show you the time for each pass. For example, in this case, I wanted to plot an image from February 20, but I didn't know the exact time that the NOAA 20 satellite passed over the Brazilian southeast region. So I checked it here and added these times on the function, and it generated this nice image for me, okay, from Tropical Storm Makara last year. And we can process this information using Python or Polar to Grid, okay? So these notebooks we share today, they are basic, but over the years, we've developed many examples with more advanced processing, and you can easily access them, create your own copy, and adapt them according to your needs. In addition to our recording introducing Google Colab and GoalsR processing, you can find a Colab notebook for basic GoalsR processing, another for more advanced processing, one covering GoalsR ABI channel differences and how to create RGBs. There's another notebook covering how to accumulate and count GLM detections and overlay this information with ABI. We have another notebook with examples on how to automatically track thunderstorms using an open source software developed here at MP. We have a very nice slide deck covering basically anything you need to know about satellite and NWP data processing with Python. We also have notebooks covering other satellites such as Sentinel-2, Meteosat third generation, and METOP satellite from EUMETSAT. And as I mentioned earlier, using a single programming language across our trainings has greatly simplified the process, and it has allowed us to combine satellite data with other sources like weather radars and NWP outputs. And with all of this, I believe we now have more than 200 example scripts freely available to the community that you can check on those links, test them directly in the cloud or locally if you want. Okay, and as Marcial will mention later, if you use these scripts as a starting point and also use AI to adapt your script, the possibilities are virtually endless. Okay, and that's it for this first session. If you try running these scripts during the hackathon, and if you encounter any issues, please don't hesitate to send me an email, and I'll be happy to answer any questions, okay? So that's it, 35 minutes. Thank you very much. Do you have any questions?
Thank you so much, Diego. And yes, a very, very quick overview, but everyone should have access to those Colab links. We will put it in the chat, and they are updated in your session and Sketch. So if you all have logged into Sketch and look at Diego's session, it will be there for you to click on and play around with. And we will get the slides up in Slack soon as well for all the presenters this week. So once we do, we'll make an announcement about that. So you have that available to you as well. Let's see. We have one question in the chat. Can you download data for a specific region using the full disk option?
No, we do not. What we have is, let me open it for you. Just a moment. Notebooks, online notebooks. Let me quickly show you. This notebook here, which is also referenced in the slide deck, one of the scripts shows how you can take the full disk and select a region for you to crop or reproject. Let me show you example number 12, cropping a full disk image, right? You have the desired extent, right? Minimum longitude, minimum latitude, maximum longitude, maximum latitude. And the script will get the full disk image and crop it according to the desired coordinates. You can do it for single bands, you can do it for RGBs, and you can also reproject the image. This image is reprojected to the equidistant cylindrical projection, and this one is on the region projection, the region goals or projection. So this is one of the notebooks available, reference it on the slide deck, and you can test it and change it the way you want. Okay, so this is totally possible. Okay.
Thanks so much, Diego.